Thus far, we have used a circle to calculate digits of pi. More specifically, we have numerically integrated the function of a circle. Using that approximation to area, we have been able to calculate pi. As a quick reminder, these are two of the methods we use to numerically integrate the function. The trapezoid rule is used in Romberg integration, which generally gives us better results than Simpson's rule. That can be seen in the data here. 14 digits of accuracy on the left versus 10 on the right. Enough with circles now. The question was asked if any other functions can be integrated to extract pi. Did you think of any? Well, circles pertain to geometry. A close cousin of that discipline is trigonometry, which has its associated functions for sine, cosine, and tangent. I have pulled this table from a previous lesson for ease of reference. Notice in red that 45 degrees is equivalent to pi over 4 radians. Do you think we could do something with that? Here is a quick reminder of an isosceles right triangle. The definition of tangent is opposite over adjacent. 1 over 1 equals 1. So tangent of pi over 4 equals 1. Next, I take the inverse tangent of both sides. This part requires exposure to calculus to fully understand. If you have taken such coursework, you should remember that the integral of 1 over 1 plus x squared is equal to inverse tangent of x. Evaluate inverse tangent at 0 and 1, then subtract. That leaves me with pi over 4. Pi over 4 is equal to the definite integral of 1 over 1 plus x squared. Multiply both sides by 4 to isolate pi on the left-hand side. In a picture, the blue curve is the function 1 over 1 plus x squared. The area beneath it, shown in pink, from 0 to 1 is equal to pi over 4. We can numerically approximate this area using Simpson's rule or Romberg integration. Those methods require us to input data. Here are the function evaluations for 1, 2, 4, and 8 panels. The same pattern continues for more panels. Using Simpson's rule, we get about 13 digits of accuracy using 128 panels. Not bad. How does that compare to numerically integrating a circle? Here are the results of Romberg integration. Unfortunately, the most accurate value is not always the rightmost entry in each row, as it was previously. I have boxed those quantities in red. As we've seen before, taking the base 10 logarithm of error gives us the number of digits of accuracy. Again, I have boxed in red the highest value in each row. Here is a side-by-side comparison of the two methods. Plotting the data looks like this. Romberg appears to outperform Simpson, but why does it flatten out? As we've seen before, I suspect we are hitting the limits of this software in terms of the number of digits it can store. That suspicion is only confirmed when I plot the data with a logarithmic scale on the x-axis. If I extrapolate to 128 panels, it looks like I could get about 16 digits of accuracy instead of 15. Not a huge gain, but this looks like a better fit for the data. A similar conclusion can be drawn by extrapolating on this semilog plot. Comparing the two methods side by side, it looks like Romberg hits 14 digits of accuracy at 64 panels. Meanwhile, Simpson gives us 13 digits at 128. How do these compare to integrating the circle? Feel free to post your thoughts or any questions you may have in the comment section below. Stick around for the next lesson. We will explore yet another function we can integrate to find digits of pi.